Is there no other questions? We'll continue. Okay.
Do we have to know how to draw the hybrids of structures?
It wouldn't be bad to know how to draw a hybrid structure. Hybrid, although you should know what a hybrid structure is. You know,
Can you go over the problem of a hybrid?
Okay.
Can we also go over electronegativity values?
Well, let me just do something really quick before we do that. The letter designation for the orbitals comes from spectroscopy. And once you get past a certain letter, F, then it kind of loses its meaning, the original meaning it had. And where is that? S does not stand for sphere. You know, a lot of people think S stands for spherical. S actually stood for sharp. The sharp lines in the spectrum. D stands for diffuse. You know, there are these broader diffuse lines in the spectrum here. And it turns out that the lines originate from the S orbitals. These ones originate from the D orbitals. P orbitals are the principal lines in the spectrum, and F are the fundamental. So S, P, D, F means something in terms of the spectrum. These are different spectra of the atoms here. Or these could even be molecular as well. So molecular, you can expect more broader ones. But once we're beyond that, then it doesn't really matter what you call it, because it doesn't really have a specific meaning to it. Now, for hybrid structures, like the one we did in class, what was the one we did in class? Have you looked at, you probably want to look at that one first. Obviously, you want to do the ones that we do in class initially, just have those mastered. So what was this one called again? This is the one we did in class. Bicarbonate. What do we call this Lewis structure here? Call this Lewis structure a resonance structure. How many resonance structures does bicarbonate have? 2. So the other resonance structure is going to look like this. We use this. What's this called here? What's that thing called? We have different ways of writing arrows. We have a way of writing it like this. We don't use this. This bottom set of arrows is reserved for something called equilibrium, which we're going to talk about more later. This top one is called I didn't write the name, I just said it. Just wrote it down. But anybody have a photographic? Very few people have photographic memories, but this one is called the double-headed arrow. Double-headed arrows are only reserved for resonance structures. This is why I talked about it at that time. but it's been a while since maybe forgot about it. Already. What does the other resonance form look like? This.
Double bond on the bottom.
Yeah, double bond on the bottom. Okay, how about a third resonance form? We actually tried to draw a third resonance form for this. What happened?
Formal charge.
Yeah, normal charges got all screwed up. So it turns out there are only two resonance forms for this. And so we're only going to average these two. When we average these two, then come up with a hybrid structure. The hybrid structure is going to be like a structure that's halfway between these two, or a 50-50 mix of those two. And so if we look at most of this molecule, it just stays the same. What's fixed? Well, what's fixed is single bonds to all of these are fixed. Two lone pairs on this oxygen are fixed. So when we draw up a hybrid structure, I look at what doesn't change. What doesn't change is two lone pairs on each oxygen. That doesn't change. What does change is the formal charge. If you have -1 on 2, then -1 on 2, we have to divide a -1 charge over 2 atoms. So each atom is only going to get -1/2. And then we have this double bond. The double bond is going to be smeared out over 2 oxygens. So what we'll do is we'll just kind of dash it out like this, smear it out. And that lone pair is going to be smeared out here. So these little dots don't represent individual electrons. It just means it's smearing the electron cloud out. So this would be kind of the hybrid structure of this.
Do you have half an electron?
Can you have half an electron? No.
So what do those -1 charges mean?
-1/2 charge means the cloud spread out this way. The -1/2 cloud just has to do with the charge densities here. So for example, here, this would be a 1.5 bond. Here. This would be a 1.5 bond here.
And the others would each be 0.5.
But you know, the other thing is that, okay, you have this cloud and distribution. And so one way of visualizing this, like say for the -1/2 is, okay, here, you know, maybe we could put one electron in one and another electron in the other, but it doesn't work that way. We can't put one electron in one electron in the other, because that would change the magnetic properties. The same thing here. We can't put, well, if we got 2 electrons, maybe we could put 1 electron here and then 1 electron here. Right? If we put 1 electron here, 1 electron here, rather than 2 electrons here and 0 electrons here, if you keep these two fixed, right? And so maybe I'll just erase one of these, put one here, and that would give it -1/2 on each. But the other way of dealing with this is that, you know, we're just going to smear out the electron cloud. And so there are different negative charge densities associated with that electron cloud. That would be the other way. And so it's a -1 charge that's smeared out over this. We call it delocalized. Right? And so it's just spread out.
So the -1/2 doesn't represent half of an electron?
Well, no, it doesn't. It doesn't represent a half an electron. What it represents is like this. This is what I showed in class that particular day. If you have 2 feet of water here, and then 1 foot of water here, say, it's 2 feet, this is 1 foot. then if I remove this wall here that's separating that, then it's going to spread out to 1.5 feet. Well, it's the same thing. The electron, you know, the problem with these is, I'll talk about it in just a little bit. The problem with these is, you know, the electron cloud, the density spreads out. And so it's not like concentrated in one spot. If it were concentrated in one spot, then you go, okay, that spot's got that full negative charge. And so if you distribute it over a wider range, a wider area, it's going to be a much smaller overall charge. But the true situation is this. The true situation is the problem with this. Lewis structures, this is what we call quantum mechanic light. It's not the full version of quantum mechanics. If we do the full version of quantum mechanics, it's called molecular orbital theory. And so what we're doing is this. We're coming up with this thing called the hybrid structure because our Lewis structures don't work. The hybrid structure is what they call an ad hoc add-on to our quantum mechanics light to make it work. Basically what happens is Lewis structures fail. They fail, therefore we have to come up with a new thing to fix it. The new thing to fix it is the hybrid structure. The hybrid structure, we just kind of smear everything out and localize it the best we can. The best is something called molecular orbital theory. In molecular orbital theory, we don't have to do this kind of stuff with the electrons and electron clouds. And so if we look at molecular orbital theory, for bicarbonate, we get a different picture of what it looks like. This quantum mechanics light version is called valence bond theory. Valence bond is the light version, MO is the full version. Valence bond, you get these things called hybrids. And the reason we still do this is because molecular orbital theory is just more complex. Let's see if I have bicarbonate. Although we do have it in their Chem 1A book. Here it is. This is what it looks like. This is from molecular orbital theory. So this is carbonic acid. This is bicarbonate. This is carbonate here. And so when we look at it, the negative charge density on both oxygens is equivalent. The negative charge density is given by the shade of red here. You can see the negative charge density varies depending on where your position. So out here, it's going to be closer to -1/2 as you go closer in. Green regions are about neutral. Blue regions are positive. Now, just because we have a positive charge, when you look at the positive charge, can you have a positive charge of plus 0.5? Is that possible? You'd think, no, it's not possible, but it is possible depending on how the electron cloud surrounds the nucleus. This is what gives hydrogen bonding such strength. what gives hydrogen bonding such strength is this, you know, let me just do a side topic here because hydrogen bonding occurs here. Hydrogen bonding occurs here. What happens here is that, is the charge on this hydrogen plus one? No, the charge on this hydrogen is what we call delta plus. Delta plus, well, what the heck is delta plus? Is delta plus 0 or plus 1? It's got to be 0 or plus 1, right? No, it's not. It's between 0 and plus 1. If we look at the actual charge on it, the actual charge on this hydrogen is like 0.4, like maybe 0.6, plus 0.6. Now, how do you get a charge of plus 0.6? How you get a charge of plus 0.6 is how the electron cloud is. This hydrogen is very simple. This hydrogen consists of a proton, which is here, like that, and an electron cloud around it. And if we look at the electron cloud, well, hydrogen is normally 0 because the electron cloud is negative, and the proton's positive. So you got this negative electron. Well, this is going to cancel each other out, right? Now, if you throw an oxygen here, what does the oxygen do? The oxygen pulls the electron cloud out. Now, as the electron cloud gets pulled towards the oxygen here, what happens is it partially exposes this proton. And so now this proton becomes what we call de-shielded, and the positive charge climbs up. It's not a full plus 1. A full plus 1, it would have been ionized, called ionized. It's going to be between 0 and 1, which we call delta plus. It has to do with the way we visualize the electron. You don't visualize it as one piece. Yeah, of course we can't have half an electron. That doesn't exist. It has to do with the way. But, you know, this is more easily visualized using full quantum mechanics.
Can you talk about like finding polarity values based on the difference of electronegativity? Like how do you determine electronegativity values?
You don't. You just read them off the table.
Oh, okay. So that's not something we have to know by looking at the periodic table?
No, well, you need to know the trend in the periodic table.
That way.
Yeah, right. If you know the trend, then you can figure out the type of bond.
Okay, because in one of the slideshows, it said, like, example, and then it said, which is more polar, this or this? And it said this because this number minus this number is greater than this one. And I was like, where did they get those numbers from?
Well, the thing is, the closer they are together, the smaller the difference. The further apart they are, the bigger the difference. They're just looking at the position, like oxygen versus well, the three most electronegative, fluorine, oxygen, and nitrogen. Then you can tell based on how far apart they are in the periodic table. Or you could just calculate the number. You know, calculating the number, you're just given the so they're tables. You can look it up. Actually, the tricky thing is there are many tables of electronegativity that we can look at. Not just one. The one that you saw is called the Pauling, from Linus Pauling. This is the Pauling scale. Pauling scale varies from 0.7 to 3.98 or 4.0. But there are many others that are more accurate than Pauling. Because Pauling is overly simplified. So here we can go. So you saw the Paulings. We have Mulliken, Allred, Sanderson, Allen. So we just use the Paulings. All the other ones are going to require more information to do. And so, then I gave you some broad cutoffs, you know, for electronegativity differences. And so, if you remember what problem that was, that we can look at it specifically.
It wasn't a problem, it was just an example. difference in electronegativity between hybrids and a hydrogen and oxygen bond and a hydrogen carbon bond. I know they got the numbers, there's like 3.4 minus 1.2 is 1.4 versus 2.6 minus 2.2 is 0.4, and I just didn't know where they got the numbers from.
Those numbers came from, they were given.
Okay.
Okay, other questions? Yeah, the electronegativities are not easy to calculate. I mean, you look at Pauling's. Pauling's is based on a lot of physics here. And the other ones are based on physics and a lot of geometry. These other ones. Well, these aren't so easy to calculate. So they're going to just like now electronegativities do change depending on the environment around the atom and the charge on the atom. And so these other ones are more accurate. You can figure out the electronegativities based on that. This is the table. This is Pauling's, by the way. Well, we just round it. For example, fluorine, 4.0. Carbon, depends on how you want to round it. Some people round it to 2.5, some people round it to 2.6. Our book rounded it to 2.6. Okay, any other questions on this?
I have a question. So for the quantum supplemental, what is that? The ones in the front, the 1 through 11?
1 through 11, the problems are at the back.
Oh, okay.
You should read it. Three and a quarter pages worth of reading.
Oh, okay, I see this one. All right.
3 1/3 pages worth of reading. And then answer the questions. There are 2 pages worth of questions or 3 pages worth of questions.
Thank you.
We're doing the labs at the end of the semester. Do you want us to fill out all the lab reports and just staple them and give them to you?
For which lab?
Because we haven't turned a few of them in now.
Yeah. Which ones specifically?
The last one, and then the third one we did. We haven't done that one.
The experiment 3. Do you guys know what I want for experiment 3? Experiment 3 is written, it's observations in your notebook. So I told everyone I'm going to just check their notebook for experiment 3. Experiment 6, you have some reactions that you have to finish those. That you got to turn in at the end. And then experiment 10, it's simple calculation. I was going to collect that one last time, but that one should only take a minute to finish. So maybe we can finish it soon and turn it in before the end. And then experiment 12, we're not quite done with.
Right.
So those are the experiments. But I don't want those all at the end. Experiment 3, I'm going to check your notebook probably at the end. Experiment 6, I want before the experiment. All right.
So we don't need to write them on the worksheets, we could just write it in our notebook.
Well, experiment 6, I don't know if anybody caught that. I said experiment 6, I changed what I wanted. Did you guys catch that or not? What was different? On the report sheet, it just wants the net ionic equation. For experiment 6, what did I want? I wanted the CE, the IE, the NIE, and the driving force for each of them. This is,
How long ago was that?
that's a long time ago, so it didn't. I wrote it down, I think, on the board, but I think not many people write things down.
Are we going to have an opportunity to clarify some of these in class if we have any questions?
If you have questions, ask me specifically about that lab, but I did write it down on the board at that time. But like I said, very few people write things.
So our labs aren't doing time soon.
No. I mean, if you need more time to complete, we didn't finish all the reactions in experiment 6, though. And so experiment 6 was unfortunately, yeah. And so what will happen with experiment 6 was, I was thinking maybe I'll have time to demo some of the ones that we didn't quite get to, but I don't think I have time to demo because we still have the redox one that's coming up. And so there's really not much there to finish, but it would be better not to turn them in all on the day of the final in case, you know.
So they should be
Not the work. You aren't going to have enough space on the worksheet for experiment 6, so I wanted that on a separate paper actually. I mean, if you could cram it in on the worksheet, go ahead and cram it in on the worksheet, but not in experiment 6. Experiment 12. Experiment 12. There was one. Do you guys remember me saying there's one additional calculation I want you to do for experiment 12?
No, it's not.
You don't remember that? There's one additional calculation I want you to do for experiment 12. And, I mean, not 12, experiment 10. You weren't here for that day, so of course you weren't here. But there, on the day of the lab, we just did part 1 of that, and so there's the calculation is very simple. You calculate the molarity of the sodium hydroxide, and then the average. And this is going to be an average of 3 trial. And actually, do you guys have it? You guys have that experiment? All right, there's one other thing I wanted to talk about that particular experiment, and that's with averages. We have to do one thing, and that is how much confidence can we have in an average? And so this is what I'm going to tack on. You know, whenever you're given an average, how good is that average? You know, like somebody asks you, what was the average score on the test? Well, the average score, sometimes you don't know something about the average. You know, you don't know this. Was everybody clustered near the average? Or was there somebody with a super high score and somebody with a super low score? You know, did most people just do average? Or did some people do very well and some people did very bad? And that's why you got that average. And so that's the spread. And so what we need to do is we need to do one more calculation to show the spread. Now we artificially held the spread tight because of the percent agreement. We did that one calculation where you calculated the biggest minus the smallest divided by the smallest times 100%. It has to agree within what percentage? Within what, 0.5% or something, right? 0.5%. Well, we made that artificial because normally we don't throw away data. Normally we keep all our data in, and then we want to look at the spread. And so whenever somebody gives you an average, we need to know what the spread is. What the spread is, and this is the final calculation, and I would have done it earlier, but we're running out of time. So let's say you got 1.23. You know, that's the average, but what was the biggest? Can you tell me what the biggest of this was? Maybe the biggest was 100, and maybe the smallest was somebody got negative 99. If somebody got negative 99 and somebody got positive 100. That's a huge spread, right? And so we don't know how the class or how you did, or maybe you got a very tight spread. Maybe all 3 of your results were clustered around 1.23. And so this final calculation is going to be a plus or minus that spread. And the plus or minus that spread, we call this the 95% confidence interval. And so we're just going to do a simple calculation. Now it's not as simple. It's a simple calculation. You just plug in the numbers into an equation, and then you're going to get this plus or minus thing that's going to tell you that with 95% confidence, 95% based on statistics based on how many runs he did, it should fall within the average should fall within that, the true average. We'll talk about that. This deals with random error, and so that's the one additional calculation. Otherwise, don't turn it in yet because you still need to do that calculation for experiment 10. All right. But there's the three outstanding labs. Is it clear? Experiment 3, what are we doing with experiment 3?
No propulsion.
Yeah, experiment 6?
Other piece of paper because you have more.
Right, what equations do I want for experiment 6? And driving force, yeah, good. And then experiment 10, we'll do this through add-on calculation.